Welcome to the second part of the inference problem in directed models or any graphical model. We have seen in the previous discussion that we can have a belief propagation or a message passing algorithm to efficiently compute this probability by means of a kind of recursive message passing algorithm. And from that you can do any inference syntax, basically compute any px given e. But the thing is that algorithm applies only to singly connected graphs. That is a graph which takes the form of a tree. You cannot have multiple paths between two nodes. Only one path is allowed between two nodes. But in general, the DAGs or any graphical model can be the factor graph model can be multiply connected. There may be multiple paths between two nodes. So the usual approach in such a case, although there is no general efficient method for solving the general case of multiply connected DAG, but there are some special cases or which are kind of approximations that can sometimes not approximations also, sometimes exact, that can be performed. The most popular algorithm is something called a junction tree algorithm. So what the junction tree algorithm does is that it clumps the variable together to create something called a supernode. So if there is when do we lose the single connectedness? When do we have multiple connectedness? When there is a small part of the graph, small subgraph, where there are a lot of connections. They are as if fully connected. So what is done is that you identify such parts with loops. You identify parts of it. Often it turns out the entire graph is more or less singly connected, but a small part of the graph is multiply connected. There are loops in that. So what you do, you lump the small parts as kind of supernodes, as kind of cluster of nodes, cluster of variables or supernodes. And so you lump clicks, variables in a clicks as supernodes, and you construct a sort of new abstracted graph, abstracted graphical model, where this group of variables are now nodes, and there are edges between only this group of variables. And if we have done this, most of the time what happens is that the resultant graph, the abstracted graph, is a singly connected graph, is a tree. Okay, so you have groups of nodes as nodes now, and edges between groups of nodes, and this abstracted graph takes the form of a tree or a singly connected graph. Once it takes the form of a tree, now you can easily do a usual belief propagation or message passing algorithm that we discussed previously on this abstracted graph. And once you have done that, so what you basically get is so now since it is a cluster of variables which is treated as a single random variable, and you get the joint probability distribution of these clusters. And if you want to marginalize on each of these clusters, then you once you using this message patching, you find the probabilities. Then within that probabilities, if you want to further marginalize, you do a full complete calculation. Note that even in a multiply connected graph, you can still do an exact inference. You can still find out the full probability. Only thing, it will not be efficient. It will take a lot of computation. So what is now done? The overall inference across the graph is done by message passing, and the local inference, which is obviously a much smaller graph, so computational complexity is not a big issue. You do a full exponential summation. So this algorithm is called the junction tree algorithm. We'll describe this algorithm in detail. There are two other algorithms. One is called a cut set algorithm or a cut set conditioning algorithm. So you have already seen previously that we can do a variable elimination. That means if we assume some nodes to be observed or constant, you clip them to a constant value, you can remove them from the graph. So what cut set does, it identifies a set of nodes which can be conditioned, that means set to a constant value or as if observed, and then you eliminate them or cut them from the graph, and the resulting graph becomes a tree, becomes a singly connected graph. The resulting graph becomes a singly connected graph. And you run the usual message passing on them. Okay, so so now the question is, this we are doing sort of virtually, you are fixing it to a constant, but you have really not observed it. If you really observed, you will actually do the conditioning. So what happens? You repeat this entire process of cut set conditioning as many times the different values, these cut variables, the variables that you have cut, they can take. Okay, so if some variable is binary, you do this twice and take the average of the joint probability over these two attempts. Usually this cut set should be small. You should be able to identify, which is again a property of real graphs, that it usually have a small cut set, which if you remove it becomes a tree. So that is what you have to find out. So you have to find out a cut set. Actually, the problem is the problem of full exact inferencing in a directed acyclic graph which is multiply connected is shown to be NP hard. So you cannot find an exact algorithm which will solve this. It's not possible to find an exact algorithm which is non-exponential and it will be solving this. It's an NP hard problem. So what this cut set conditioning and other do is that they assume a special case of the graphs where the cut set is small, or there are few clicks, as in the junction tree algorithm. Otherwise, this will take a lot of time. Because it is an NP-hard problem, I think it follows that the general finding out the cut set for a full graph is itself a hard problem. The third thing is that third approach is something called a loopy belief propagation. So in normal belief propagation, there are no loops. There is an upstream set and a downstream set, and there are no loops between you can easily cut out the upstream and downstream if you remove X, the intermediate node. But in this case, they are not defined if a multiply connected DAG. So what you do, assume that it's singly connected and do carry on with your belief propagation as before, but in a loop. You do it over iterations. You do once, again do once, you do it in a loop, the belief propagation, with the hope that this will converge to a value after some iterations. So there is no guarantee for convergence of this except for certain special graphs, but works well in practice. Okay, so in fact, there is a very nice similarity of this to a error correcting code and turbo decoding method that is sometimes done in data compression and other things. Okay, so I'll only deal with the first algorithm. These two are actually loopy belief propagation is basically belief propagation run over loops. Cut set conditioning requires more knowledge of more advanced algorithms. I'll not go into it. Let me explain the junction tree algorithm. So what I'll do in the junction tree algorithm is I'll describe a method which will convert a multiply connected DAG to a singly connected DAG by lumping some of the variables. And I'll describe that process. And once it becomes singly connected, then you follow the previous procedure of belief propagation. Okay, so the algorithm is like this. You are given a multiply connected DAG. Here is an example with directed edges. First thing you do is remove all the directions, remove all the arrows in the edges. So you remove all the arrows, then introduce additional links, additional edges by a process known as moralization. So what the moralization does is that for every node, look at the parents. If the parents are, for example, here, you look at the parents. D has only one parent, E has only one parent, F has two parents, C and D. C has two parents, A and B. So what the moralization does is that introduce for every node, find out what its parents are, introduce edges connecting every pair of parents. So here there will be, for C there will be edge between A and B, and for F there will be an edge between C and E. Okay, so this is the moralization. So I join A and B, I join C and E. This is called moralization. Of course, I after this I remove the edge directions. The purpose of doing this is that this additional, since you have removed the directions, these additional links sort of directly encode the indirect influences, the conditional influence independences. It indirectly encodes the, so in this, after this moralization, the final graph you get, you need not look at deseparation or anything. You can immediately find out the conditional independences as given by the graph itself locally by looking at just the neighbors of a node. Whatever conditional independences you get, that's enough. No additional independences are there. Okay, so there is a equivalence between the IMAP of this undirected graph and the IMAP of this moralized graph. Both of them have the same IMAP. They refer to the same, they encode the same conditional independences. There is one more step, you do a triangulation. So you find out all loops of length greater than 3. Find out all loops of length greater than 3. If there is such a loop, you introduce chords so that there is no loop of length greater than 3. For example, if this red link was not there, BCED would have been a for loop. But if I introduce the CD chord, I get only smaller loops. I get BCD loops and CDE loops. So there are no loops in this graph which are more than length 3. If it is more, I short circuit them by introducing a chord. Okay, so this final graph after this moralization and triangulation and undirection, with this graph, we do the step 4 of the junction tree algorithm, which is find the cliques in this graph. Cliques means it's a complete graph. It's a subgraph which is completely connected. Every node is connected to everybody else. So you find the cliques. So here there are 1 click, 2 click, 3 click, 4 clicks. ABC is a click, CD is a click, CFE is a click, CDE is a click. So you find out all the clicks in this graph. Each of these clicks in this graph are a supernode in the abstracted graph. Each of the clicks in this graph are a supernode in the abstracted graph. So if we look at the clicks ABC, BCD, CDE, CFE. ABC, BCD, CDE, CFE, CEF, CFE. Okay, so this is the abstracted graph. You see, these are supernodes and there are edges between them. Now I'll tell you what these edges mean. So what I'll do is that if two of these nodes here have some overlapping variables. For example, ABC and BCD has overlapping variables BC. Okay, so what I will do is that I'll introduce an extra factor, a box here, which is the intersection between these two nodes. Okay, which is the intersection between these two nodes. Rather, the actual property is known as something called a running intersection property. Okay, so if a variable appears in more than one click, so this is a click. This note that every node here, every super node here corresponds to a click in this triangulated and moralized graph. It corresponds to a click. So if there are 2 clicks which share 2 nodes, all the intermediate clicks in the path from one click to the other click should contain those overlapping variables, right? So this is required. I mean, of course, I'm not explaining it. This is required that so that the neighboring clicks, because you see if you look at the joint distribution between C, D, and E, and the joint distribution between C, F, and E, these two are two overlapping clicks. This joint distribution should have a type of consistency. That means if you marginalize CD from one of the clicks, and if you marginalize CD from the other clicks, these two joint distribution, these two marginalized CD distributions should be identical. Okay, so you can marginalize over E to get a CD distribution from this blue click. You can marginalize over F to get this C distribution over this green click. And these two both are C, so both of them should be the same. They should agree. Okay, so this should be ensured. So this running intersection property basically ensures that. All right, so this is the entire algorithm. So once you have done this, then it's simple. Then what you do is that now you look at this. This is a factor graph which is singly connected. This is a factor graph which is singly connected. And you run your belief propagation algorithm over this factor graph. You estimate the distributions, whatever. But now you can estimate distributions over this cluster of variables A, B, C, not over individually A, individually C. You have to find this probability inference. You can do only over clusters A, B, C, only over clusters B, C, D. Okay, you do that. And if you further want on individual A, you look at ABC and then do a marginalization over ABC. It will take some steps, but anyway, ABC is a small set, so you should not worry about doing the full summation. Anyway, it will not take much of step. But doing the full summation over the entire set of 6 variables would have taken much more time, rather than summation over just A, B, and C. So this is the junction tree algorithm. Basically, you convert to a singly connected tree, singly connected DAG, and do the belief propagation. And these are the graph theoretic steps that I discussed, explained in the junction tree algorithm for doing this. Similarly, there is a cut set algorithm which is even more complex. I am not going into that. Those who know algorithms, graph algorithms well might know the cut set algorithms. All right, so now these two are again kind of exact inference. That means even though I have prepared this junction tree, I have made supernodes, but within the supernodes I am doing full summation. So finally, I will end up with a actual distribution, exact distribution. Okay. Only thing, the time complexity, the more it is close to a singly connected graph, less and less clicks will be there. So you have this final graph is smaller and so on. But more it is away from a singly connected graph, it will take more time. But final result will be exact inference. But we can also sometimes do with approximate inference. That means don't go into all this graph theory. We have already studied 2 approximate inference method, one by sampling, Markov chain Monte Carlo, and one by variational inference. Approximate the actual distribution by a simpler distribution, either by mean field approximation. In fact, this loopy belief propagation that we have talked about in this lecture it can be shown to be a type of variational inference. You see, you are doing a belief propagation per iteration. It's like the EM algorithm. It's like the variational algorithms. Okay, so this is a kind of variational inference. I'm not going into that. It involves a pretty bit of derivations to find out that. But let me explain the Gibbs sampling or the MCMC, Markov chain Monte Carlo method. Note that both these methods, as we have also discussed previously, will only give you the approximate result of the query, of the inference query. It will, if you want to find Px given E, you will find something P tilde x given B, which is close to Px given E. Okay, so let's see the Gibbs sampling. We have we basically know what is Gibbs sampling. Let me explain it for the graphical model. The steps are as follows. Suppose I have a graphical model with variables x1 to xn. Initialize the variables with any value in their domain. Any value in the domain of x1 to xn, you initialize them with. And then till you reach convergence, I'll explain what convergence means. You do the following. So you already know a value of x1, x2, x3, xn. Pick some ordering of these n variables. Say x1, x3, x2, x5, x7, some ordering of these n variables you pick up. Okay. Usually it is better to pick up a ordering which is in the same topological sorting order as the directed acyclic graph. Now sample one of the variables, let's say xi variable. So you imagine your directed acyclic graph, just pick up any variable. I'll explain with an example soon. Pick up any variable xi and sample from this conditional distribution pxi given all other variables. So as if you have a graphical model, you have fixed values of all the variables except one. You have fixed values of all the variables except one. Let me explain again with this old example. Yeah, here is my example. So what I do is that, let's say I fix some value. Okay, I fix difficulty to be say high, intelligence to be high, SAT score to be high, letter to be good. And I don't fix a value for grade. Except for grade, for every other variable, I fix a value. Now, because see, for every other variable you have fixed a value, looking at the conditional probability table of this grade variable, since all other values are fixed, they corresponding to some rows in this CPT. And they have some probability values. So as if all these probability values define a distribution over possible values of grade. Maybe, for example, if you fix difficulty to be high and difficulty to be low and intelligence to be high, the probability that grade is good is say 0.9 and the grade is low is 0.1. Okay, given these values, the difficulty is low and intelligence is high. So grade good is 0.9. Sample the value of grade according to this probability, 0.9, 0.1. Sample a value of grade by coin tossing or throw up dice, whatever. You sample a value and assign that value to grade. Now do your Gibbs sampling. Okay, so sample x, fix that value, update xi to x. Now move on to another variable, let's say x20. Fix all other variable, but now don't for all other variable the fixed value is not the initialized value. For one of the variables it is this updated value, this new sample that I have drawn. And again sample. So for example, grade I already know to be high, fix grade to be high, and now you want to find the recommendation. The difficulty is still low, intelligence is still high, SAT is still high. You find the letter of recommendation, say 0.8 high, 0.2 low. You sample. Let's say you get a X recommendation to be high. Pick up that value, fix that value, assign that value, update that value. And keep on doing this over all the variables over several iterations till over successive iteration, these values don't change. Over successive iteration, the assigned values to each of the variables, they don't change. Okay, so once you have done this, and then if you count how many times, so you want to find Px given E. Okay, one more thing, the observed variables anyway you fix. That need not be initialized. Observed variables is always constant to the value that you have observed, the evidences. And rest of the variables, if you do it several times, and for each of the value in the domain, say grade equal to high or grade equal to low, you find out the fraction of times this has happened. The grade is high or grade is low, given the evidence values, because evidence values are already fixed. And that fraction you use as your probability. You can show, since this is Gibbs sampling, you can show that this always converges. Okay, so here let's take this example. So this is another famous Bayesian network proposed by Julia Pearl. So somebody is working in an office. His home, there is an alarm. Alarm may go off either in the case of burglary with certain probability, or in the case of an earthquake. And there are two neighbors of that person, John and Mary. If the alarm goes off, John calls with certain probability, and Mary also calls with certain probability, may or may not call. John also may or may not call. These are the CPT. Now you can have insurrencing talks. For example, suppose Mary calls you. What is the probability that there is a burglary? Okay, so let us see how do you do it. And each of these have binary values. So burglary may or may not happen, earthquake may or may not happen, alarm may go off or not. So each of these are binary. I represent these variables by B, E, A, J, and M. So initially, let's say at iteration 0 of the Gibbs sampling, let's initialize all of them to false, binary false. Now, if it is binary false, then if I sampling from B given A and E, okay, so B given A and E is PA given B and E into PB. So you put these values here, you compute these quantities, and you get this, because you already have these values. Okay, you already have these values. Okay, so you can just look up the tables and compute these probabilities. PB given A and E, and so on. You can always find these probabilities. Suppose this probability turns out to be 0.006 and 0.9980. Probability that B is true is 0.006 and B is false is 0.9980. Do a coin toss according to this ratio. Of course, it will turn out false most of the time. So you set B to be false again. Now look at another variable. Let's look at earthquake, E. So using Bayes rule again, E is this, and AB is FF already. So the current value of these variables are F and FFFF. So this green F and of this top F. Plug in these values in the CPT, apply this rule, you get these probabilities for earthquake equal to true and earthquake equal to false. Again here the probability of earthquake equal to false is much higher, but maybe by coin toss or something it turns out to be true. So you put true for earthquake. So this is the new assignment. So now using FT, FFF, FT and FFF, you now find out these probabilities for alarm. So what is the probability that alarm equal to T given the rest of the variables are FT, FFF according to that, consistent with that. So this variable turns out to be 0.66 and 0.008. So note that these are only proportional. These are not probabilities. These are ratios. They are not normalized. But that's all you need for a coin toss. So you coin toss, maybe it turns out to be false again. So you put false here. Now move on to the next variable, J given A. J given A, you can directly find out through these probabilities. Let's say you coin toss, you get true, you put true. And similarly, you get false here for Mary calls or not. Okay, so this is the new set of assignments that I have got. And I do this repeated several number of times. And these are the new assignments I keep on getting. Let's say these are the assignments I keep on getting. Okay, so now you can, so as if from this table, now I can answer any query. For example, I want to answer the query that what is the probability that Mary calls given there is burglary. Mary calls given there is burglary. So what do? You pick up the rows in which burglary is true. These are the 2 rows, out of which you find how many times Mary calls. Mary calls 1 out of 2 times. So the probability is 0.5. Okay, so from this table, you just compute the frequencies and take the ratios. So it is 1 out of 2. So that's what Mary calls when there is a burglary. So any inference query you can basically find out from the table. But I think one thing you have already observed is that if a query involves a combination which is this is by no way a full table. There may be some combinations which you have not observed in this Gibbs sampling process. So you cannot answer queries to them. But the idea is if you keep on doing Gibbs sampling for a long time, eventually you will get a good estimate from these frequencies. They will converge to the actual probabilities, just like any Gibbs sampling method. But they are slow, just like any Gibbs sampling method again. Okay, so this is the idea. This is actually a very commonly practiced method in really large Bayesian networks. Okay, so in summary, Bayesian networks are an elegant method for probabilistic modeling. They have a lot of factorization and independences. You can do exact inference, message passing, or junction tree for multiply corrected graphs, or you can do approximate inferencing. I have described Gibbs sampling. There are more intelligent techniques. There are variational techniques. There are metropolis testings also for this. So you can have several, and you can have variational inference. The loopy belief propagation, that's actually an instance of variational inference. It's an instant of variational inference. In fact, if you remember, in variational inference, we are minimizing the KL divergence between the actual distribution and a simplified set of distributions. Here we do the opposite. The KL divergence is unsymmetric. You do the opposite. You do between the simpler distribution and the actual distribution. And you can show that this loopy belief propagation does do that. Okay, so in the next class, we will move to the probabilistic, the learning of probabilistic graphical models. So I stop here. I finish inferencing here.